Hello and welcome to my video on the general tools and tricks of a proof by contradiction. Hopefully in this video I will demonstrate through example how to do a proof by contradiction using as little background information as possible, break down each step to explain what I'm doing and why, and then conclude. The aim of that is to be or to have this video accessible by as many people as possible, so it can be accessed by as many people as possible. Okay, so first things first is I want to prove that the square root of 2 is irrational. Classic problem, a textbook problem, if you may. One thing you might be less familiar with is the actual steps and the reasons why we take those steps. Even if you're familiar with the proof, hopefully I can provide some additional insights that you might not be familiar with. Okay? Okay, so the first order of business, to keep in line with what I said previously, is to define what irrational means. And to do that, I'd like to go through some additional definitions. So the first one is this one. An integer is a whole number and can be written, or can be positive or negative. So what I mean by this is a whole number, let's call it W for whole number, is equal to a set of numbers 0, 1. The 0 sometimes is a bit controversial, but I'm adding it here. 1, 2. But we're adding in this additional term, not term. We're adding in this additional restriction of it has to be positive or negative. So we will put this as, that's the natural numbers, sorry, as the integer class, which is written as such, where you go from negative infinity and then -2, -1, 0, 1, 2, and all the way to infinity. So that's what a whole number is. Just it's a natural number, 0, 1, 2, and so on, countable numbers. But with this added restriction of it can be positive or negative, we then get the integers. Okay, so then the next definition I'd like to go through is what a rational number is. And a rational number is a number such that, this is what this colon means, such that it can be written in the form a divided by b. This is just, it's very poorly drawn, but this is just the rational, the class of rational numbers symbol. And we also add that r cannot be simplified further. And the third definition is that an irrational number is a number such that it cannot be written as a divided by b. So it's all of the real numbers, so that includes all your decimal place points and whatnot, which cannot be written like this. That's what an irrational number is. And we say that r cannot be simplified further, but that's somewhat redundant. Okay, so now we can tackle our problem. Prove that the square root of 2 is irrational. So I'll go through the proof and try and write down my steps along the way. So step 1 of any proof by contradiction, assume the logically opposite binary choice. What I mean by that is we have that prove that the square root of 2 is irrational. So we want to assume, or square root of 2 is either rational or irrational. We will assume, because we're doing proof by contradiction, that it's not irrational. So assume square root of 2 is not irrational. Therefore, square root of 2 is rational. Okay? That's step 1. Step 2, we will then attempt a direct proof for the above assumption. Okay? So what I mean by that is we've got our definition of irrational, and we're saying it's not irrational. We're assuming that. So that means then we can write the square root of 2 as some a divided by b, which by definition cannot be simplified further. So we have square root of 2 is equal to a divided by b for some integers a and b. And what this means, by the way, this is just mathematical class notation. Sounds scary, it's really not. I'm saying these terms a and b, and they can be anything, as long as they are elements, and this is what this symbol means. It's what this symbol means here. Oh dear, I accidentally crossed the line through it. It's what this symbol means here. A and B are elements of the integers, which is what I've got here. So just any whole number, positive or negative. Okay? But from this, what we can do is we can square both sides. Why not? It keeps both sides happy. So we can say that, where is it? There we go. Is it this? This pen. Therefore, if you square both sides, we get that 2 is equal to a squared over b squared. Now I'm going to times both sides by b squared, which is the same as just plonking that up here. Plonking this b squared term up here. So we get that 2b squared is equal to a squared. So from this we can see that if we were to move this 2 to divide this a squared, well then a squared divided by 2 would equal b squared, and what that tells me is that because b is an integer, b squared must also be an integer. In fact, a whole natural number, but an integer, which means that a squared divided by 2 must be an integer. So 2 must divide a squared. So I'll write it a little clearly. A squared must be even. And I know that any even number squared makes an even squared number. A little proof of that is, say if I took, oh, I don't know, let's do this in a different colour. Let's choose pink. If I choose Q, let's go with the integers. such that q is even. Okay? So k and q are integers such that q equals to 2k. If I square both sides, I get q squared equals to 4k squared, which equals to 2 times 2k squared, which means that q squared divided by 2 gives me 2k squared, an integer. K is an integer, so k squared must be an integer, times by 2, it's still an integer. So 2 wholly divides q squared. And that's a direct proof that all even numbers squared produce even squared numbers. Okay, so back to the proof. Little side tangent there, sorry. But it's useful because now we can say that A, if K, I'll use a different letter because that's from a different thing. Let's use, I don't know, F is an integer such that A equals 2F. I'm just saying that A is even. We can say this because we have that A squared is even, and we've just proven that any even number squared is a even squared number. So what I'm going to do is I'm going to sub this, naming it equation 2, and this equation 1. I'm going to sub this into here, so that we get that the square root of 2. No, sorry, I want to use this equation. Do I? Why not? Let's use this. Sorry, I know I keep changing it. I'm using this equation. So then we have 2b squared is equal to 2f squared. All of that squared. So that equals 4f squared. But I can divide both sides by 2 to give me b squared equals 2f squared. Ah! What do we see here? Similarly to what we said here in this top section, we concluded that a squared must be even because we have this 2 times b squared. And what do we have here? We have b squared equals 2 times f squared. So then we say, let me write it more explicitly, b squared must be even. Can you see the problem? Well, this implies that we can write b as some integer, write that a little neater, integer g, we can write b as some positive number. And we know that because of the above proof. Okay? But this is where the problem lies. We have, let's put everything together. We have said that the square root, this implies that the square root of 2, which is equal to a over b, is also equal to, we have our value of a as 2f divided by 2g. Okay? Goes without saying, I should say it actually. I'll write it here. A, F, B, G are distinct primes. Distinct integers. They're not equal. And I have implicitly assumed that all throughout. Okay? Well, I haven't assumed it. I've stated that is what it is by definition. They are not the same integers. There can be any integers as long as they're not the same. I've also, by the way, because it breaks maths if you do it, that b is non-zero. It's not equal to 0 because if we divided a by 0, math starts to break, and I don't want to do that. So then we can go back to this and say that f over g. I've shown that they must be equal for this to work, but they're not. So the definition can't break because that's by definition. What must break then is our assumption that the square root of 2 is not irrational, because that's the only other thing that we've assumed. Therefore, base assumption does not hold. And our base assumption tells us the square root of 2 is not irrational. The only other option, if that doesn't hold, is that therefore the square root of 2 is irrational. And there we have it. So what I've done, which is very, very typical of a proof by contradiction, is we want to show that the square root of 2 is irrational. That's in the forefront of our mind. The first step you do in a proof by contradiction is to assume the logically opposite binary statement of what you want to prove. So, and I've wrote it explicitly here, that the square root of 2 is not irrational. And because of the definition of what an irrational number is, that means then we want to show that the square root of 2 is rational. The next step then is assuming that our assumption is true, which we naturally do because why would you make the assumption otherwise, is then do a direct proof. Plug in the form of a rational number as equaling the square root of 2 for some integers a and b. Squared both sides, move the b squared next to the 2 to give us this a squared equals to 2 times b squared, which gives us that a squared must be even, because I can divide both sides by 2 and I still get an integer back. I then showed that any even number squared is also divisible by 2, meaning it's even, always even. So therefore a must be even. Let me write that. A must be even, which gives us this. This is the form of an even number, which I showed here. I then substituted equation 2, this a equals to 2f, into my equation 1, 2b squared equals a squared. Expanded the brackets, give me 4f squared equals to 2b squared, divided both sides by 2, which gives me b squared equals to 2f squared. Using the same logic as earlier, b squared must also be even. I'll add it here as well. B must also be even. just using the same logic, using this proof in pink, conclude that b must also be even. I plug everything back into our original equation that we are interested in. But we notice that we can simplify this further. But rational numbers of the form AB cannot be simplified further, so our base assumption does not hold. It cannot be rational. So the other logically opposite binary choice is that it must be rational. Okay, I believe, if you do not have any further questions in the comments, that this covers the essentials of how to do a proof by contradiction. Please, 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 if you have any questions, want me to do a follow-up video, comment down in the comment section below. I will be prioritizing suggestions from my Patreon account, so please support me on there if you want to see more videos like this. And that'll be all. Thank you very much for watching.